Okay, so today we are going to do two things. First, we will talk about some of the important topics in deep learning. Couple of things in particular: batch normalization followed by dropout. So these two things are very widely used to train modern deep neural networks, and they're basically very effective to train any deep neural network. And secondly, I will talk a couple of other regularization techniques to improve the deep neural network model's performance, to make it robust in terms of generalization and all. And then I will start talking about the Bayesian classifier. So the classifiers that we have seen so far is of different kind, but today we're going to see how Bayesian statistics can be used to classify the data points. Okay, it's another kind of classifier, the same thing that you could do, but using a different approach. Okay, so let's start with one of the most important part in modern deep nets called batch normalization. Okay, and the name suggests that it is basically a normalization scheme. Okay, but a particular way we do normalization. Okay. So let's take a quick look at the structure of nets. So what we learned so far, what we have seen so far is that you have the feature vectors, the input layer, and then you basically do forward pass, compute all these inputs and outputs from each of these nodes, each of these neurons, and then you simply go and predict this thing. Okay, so that is how we are doing this thing. Okay, we are straight away passing this information that you are the activation values of the neurons in the individual layers, and then we simply pass along this value to the next layer, and it will do this job. Okay, that is how we are doing this right now. Okay, now people have identified some of the problems with this, in particular when you are doing deep neural networks, because you are going through multiple transformation. Okay, in the sense that when you are passing information from first layer to second layer, this is one level of transformation is happening. You are doing some kind of transformation. From second to third, you are doing another kind of transformation. Third to fourth, another kind of transformation, and so on and so forth. Okay, so the deeper the network, the number of transformation is also going to be very, very high. Okay, and as a result, even if you are putting these input values which are normalized, but still because of this multiple transformation, the deep net still not able to maintain that normalization things after every layer. So that is exactly precisely the purpose, that we want to normalize these values after every layer, so that we do not have this kind of problem. And so the name that term, coined by the creator of this idea, is called internal covariance shift. Okay, so what it is, that each layer, as I mentioned, each layer of a network has inputs with a corresponding distribution. So when you are taking like values from one layer to another layer, which that values that basically given by one layer, I am calling this an input values. So they have a particular distribution. Now it depends on two things. Number one, you remember that you initialize these parameters randomly, okay, using a particular mechanism, Xavier initialization or Kemming initialization that we have seen. Okay, so of course these values will depend on this randomness in the parameter initialization. Number one. Number two, there is always some element of randomness in the input data also. Okay, so these two things actually can shift the distribution of the this neuron that you are getting from each in each layer. Okay, and so this effect, that internal layers during training, okay, the internal layers, this kind of distributional effect that you are seeing is called the internal covariance shift. That's the name basically they have termed it. Okay, So through this particular mechanism, the batch normalization, we would like to address this internal covariance shift. Now, this is the terminology that the inventors coined initially, but later on some follow-up papers, they experimented and have seen that probably internal covariance shift is not the right reason, but still batch normalization works pretty well. Okay, so there might be debate whether this is because internal covariance shift or not. That might be debate on that, but the fact of the matter is that batch normalization is still one of the most effective technique to kind of improve the performance of deep neural network. And it's a pretty simple technique, just normalization scheme. And let's see how it works. Okay. Now quickly, so what happens in this case is that, so the idea is this, that we would like to normalize distribution of each input feature. So by input feature, what I mean is that, for example, you are computing some values from here, right? That's the activation value from this particular neuron. From activation values from this particular neuron. Okay, so these values you are sending to the next layer. Okay, so I am calling the values, the activation values that is coming out of this particular layer, I'm calling the input for this particular layer. Okay, so that is the way basically I'm going to define it. And so what we need to do, we need to normalize the distribution of each input feature and for each layer and for across all mini batches. So you remember that we are taking the mini batches. In the next slide I have the formula and everything, so things will be clearer to you. But what we want to do, for every layer, okay, for every layer, from this layer to this layer, from this layer to this layer, and so on and so forth. Once we have the activation values from every layer, which is passing along to the next layer, we want to normalize these values. Okay, normalize my normal distribution 0, 1. And we want to do this normalization based on the mini batch that we are dealing with. Okay, that's the main idea. For every mini batch, we want to normalize these values before we pass along this value to the next layer. And not only about normalization, we do a little bit of modification, which is called scale and shift. So once we have the normalized values, we can do a little bit of a multiplication and addition and things like this with some other parameters, which is called scale and shift. Okay, so here is this actual stuff that's going on. So okay, so if you look at this particular kind of picture carefully, and here is the actual computation that I am showing you. Okay, so how to do this normalization? Now basically there are 4 things we have to do. The first thing that basically I'm saying this has to be done per mini batch. Okay, now here what you can see, the M is equals to number of mini batch, number of samples, rather mini batch size, not mini batch, it's basically mini batch size. Okay, so it's mini batch size. Okay, now let's take one by one and then we'll try to understand what is happening here. Now, okay, now let's look at this particular equation. What I am doing in this case, I'm simply computing the mini batch mean. And here this xi, and I'm basically showing for one layer, you can do for other layers as well. Okay, for the timing, assume that I'm doing for only for one layer, and same thing you can apply for every layer. So here the xi means, for example, if you consider this particular layer, so xi means, for example, because there are m samples in a mini batch, so from this particular neuron, for every sample you are going to get one particular value. Okay, so for example, xi referring to, or rather this one, x referring to this particular value that coming out of this particular node, of a particular neuron. So because I have m mini batches, mini batch of size m, then I am going to get m values from this, because for one sample I am going to get one value, so I am going to get m values for this one. Okay, similarly I will also get m values for this one. So I'm just, this formula is only for just to show you that how to compute things for only one neuron, for example this one. Okay, and then you can apply the same thing for other neurons as well. So here what I'm doing, because my mini batch size is m, I have m samples, so this particular neuron is going to give m values. So basically this is the mean of that value. Okay, so every input will be normalized, okay, per mini batch. Now this is the mean because we mentioned that it has to be a normal 0-1 distribution. So then second is the variance, the same variance that you use, the same variance formula because you have the m values and then you do it. Then third is basically once you have the mean and variance, then you can do the normalization things. And here you can see this kind of smoothing parameter just to avoid zero division stuff in case. Okay, that is why you do it. So this basically, so up to this one you normalize this thing. And now in the fourth you can see is the scale and shift which I mentioned. Okay, so what it is? Now essentially you are getting the normalized values here. So xi is the normalized value. Okay, that is coming from the previous case. So you are just multiplying with some two more parameters, gamma and beta. Okay, that is it. Now, and these gamma and beta, they are additional to parameters which you are introducing in this model apart from the weights and biases that you have. Okay, and of course because these are parameters, so you can always use backpropagation algorithm to kind of train these parameters. Okay, we will see formula in the next slide how we can do kind of backpropagation to compute the partial derivatives. Okay, so that is how basically we are going to apply this thing. So after applying all this thing, for each layer, for each neuron, okay, and for each mini batch, we are going to get the values from this particular neuron. Okay, and you can apply this for all the layers that you have in this case. Okay. So essentially, I'm trying to kind of normalize the distribution of the activation values, the output values coming from a particular neuron, which I will pass along to the next layer. Okay, and that is how basically I'm doing it. Okay. Now, so this basically, so more or less this formula that we have here. Now, quickly, just you can. These are like simple derivatives. I'm just showing you in case like you wanted to know it. So because we have this formula here on the left side, and we can straight away apply to kind of compute the partial derivatives of all the things here. So remember that the x cap here depends on the activation values. So you need to compute. So here the L denotes the loss function. Okay, loss or error function. Loss function or error function. Okay. So here this one partial derivative of the loss with respect to this x cap. This one partial derivative of the loss with respect to the variance. This partial derivative loss with respect to the mean. Partial derivative of the loss with respect to this xi, which is the activation value that you have, and then you have additional two parameters, the gamma and beta, scale and shift parameter. Okay, so you just straightforward, you can do it offline. Okay, I'm just writing down this formula, you can just cross verify later on. Just straightforward chain rule that you can apply and get it done.
Sir, why do you need gamma and beta here?
Sorry, what?
Why do you need gamma and beta here? Like
because
why
gamma and beta. Oh, sorry. The reason gamma and beta is okay. Yeah, that's a good question. Okay. So the reason, so to be very honest, I don't understand very clearly why this is the case, but I'm just quoting from the paper. Okay. So the reason that he introduced these two parameters is because of normalization. Okay, you are again now before that you have the activation values coming from multiple transformation. And because of normalization, you probably are hampering this activation values a little bit. So in order to this, the kind of error correction thing, you are doing this kind of gamma and beta transformation. Okay. So that is
why
yeah.
okay.
Go ahead.
So YIs are not the actual outputs like the XI thing. The actual output value, those are not the YIs. These are the only scaled when we are scaling.
Yeah, so yeah, exactly. So this here, this XI means this activation values coming out of this particular neuron, and so on. Okay, and YI after applying this, some operation with XI, you are getting YI.
Okay.
Okay. Yeah. So these are not input. So in a sense, you can think about like, so the output from this layer will go input to this particular layer. So that is why I am just referring to X. So basically, I took this picture from the paper itself, the original paper itself. That's the notation that they used.
Okay, sir.
Okay. Yeah. Okay.
Sir?
Yeah, go ahead.
Sir, XI is after applying activation function or before that?
After activation function.
Okay, sir.
So basically, so the output from one layer is being treated as the input to the next layer. So that is why I'm saying this the activation values, after the activation values, of course. Okay. Okay, so this is one of the very powerful component in modern deep nets. It was not well known before like 10-15 years ago, but this is like, you probably will see that everywhere when you are building deep nets, everywhere you have to use batch normalization to improve the performance. Okay, so all right. So next but what we talked about so far, during training time you are doing all these things, right? You are kind of trying to address this issue, take derivatives, compute all these things and so on and so forth. But what happens during test time? Okay, at test time you see only one example, right? You're taking one example and then testing it. So therefore, when you are testing it, in order to infer, you need to have these values, these means and variance, right? For every layer, you need to have that kind of thing. Okay. So where do we get this from? This means and variance. So what we do basically, we actually remember this means and variance from the training sample. In a sense, the population statistics of these training samples that you remember. So what we do, we simply run a moving average across all mini batches of the entire training samples. We are basically, when we are taking the mini batches, we are computing these means and variance and everything from every layer. Okay, then you simply take a moving average of these mini batches to kind of sum up with the mean and variance per layer, and you simply save it once the training is done. And when test sample is coming in, you simply reuse those values. Okay, because for a test sample, like single sample or whatever, this mean and variance on the test sample doesn't make any sense. So you simply use whatever you have learned from the training samples and you simply reuse it directly. Okay.
So why do we need mean and variance for the test samples? Because we won't be applying batch normalization in test data set, right? That's only for training.
Yeah, but when you are doing this thing, you are going through multiple transformation, right? So you are computing this x cap, y cap. You have to do that in order to finally infer the value of z. Okay, because there is gamma, beta, everything that you learned. So you have to use exact the same transformation that you have used during training. The transformation has to be consistent between test and training.
Understood.
Right? Yeah. Okay. So yeah, so just as a kind of suggestion, whenever you are building a deep nets, for shallow nets probably that is not going to make much of a difference. But when you are building a deep nets, make sure that at least you play with the batch normalization thing. Okay, you just try to add it. Not sure whether in the last lab they have covered batch normalization. Did they? The TA? Did the TA cover batch normalization in the last lab?
I don't think so.
No, sir. No, sir.
No,
Okay.
sir.
Yeah. So hopefully in the next, I already mentioned to him that he is going to cover that in the next lab, how to do it. So, okay. All right. So now quickly we move on the other thing called regularization. Anyway, batch normalization is a kind of so people say initially said that this is done to address the internal covariance shift and all, but it was found later on that this actually does some kind of regularization. So regularization means like you regularize this model so as to it's not going to perform very poorly on the test data. So here is what is this kind of the thing that we do in regularization. So the purpose of regularization, or at least in particular slide, is that you want to improve single model performance. Okay, probably you have heard of cross validation approach of improving the model. So in cross validation, what you do, you randomly split a data. Okay, multiple folds, multiple sets, 10, 20, whatever. And then basically you run or you train your model multiple times. So you keep only one set set as a test set, remaining set as trend set. You simply train it multiple times and simply take the average of it as a kind of final performance. That's what you do in cross validation. Okay. So that means running multiple times, training multiple times a particular model. But in this case, the kind of regularization we are talking about is improving single model performance. You only train once, okay, only build only one model, and based on that you simply want to infer. Okay. So here is a little picture, and probably you will encounter it now and then when you deal with real data. Is that on the left side I have the trend loss. Okay, x-axis is the epoch or the iteration, and y-axis is the trend loss value. Okay. So as you can see, when you are training, you generally observe this kind of phenomenon that as you increase the number of iteration, you're going to see the decreasing value of loss. Okay, loss value, something like that. Okay. Okay, all right. Now, what happens when you apply this on say validation dataset, test dataset? Okay. Now you see that training loss is very good, actually, not an issue. But when you apply the validation dataset, you are going to see a big performance gap. The performance is actually falling down. Okay, and the gap is becoming very, very large. So this kind of situation you will probably encounter now and then if you do not design your neural network, or for that matter any machine learning model very well. Okay, so you need to have some kind of regularization, and this is a problem that I already mentioned in one of this lecture, that overfitting is one of the main reason. Okay, you simply build very complex model, more complex than what was actually required, and as a result you are going to get this kind of issues. Okay. So,
sir, a small question.
Yeah, sure. Go ahead.
In the sir, in the accuracy diagram, what is the x-axis represents the number of training data? Is it?
X-axis represent the number of
epochs, maybe.
No, this is number of epochs actually. Right? This is number of epochs.
Okay, so the overfitting can happen like with
so
the
here I am using the validation data set, right? Training and validation data set to kind of check the performance, how it is actually doing that. So you training this one, and then on validation set you basically applying that. So what I'm trying to say here, you are training your model, so you are at, say, for example, 2500 epoch. Whatever you got from the training data set, you apply that on validation data set. What is the performance? Similarly, you do it for 5000 at 5000 epoch. You got a training model, trend model, then you apply that thing on the validation data set. What's the performance? Something like this. Okay. So you are applying essentially the trained model at different epoch on the validation data set and seeing how the performance actually of this model. Make sense?
Okay, sir.
Okay. Yeah. Okay. All right. So yeah. So what you want to do in regularization, and probably you have heard of these things. Quickly I've run through. So one of these, the main idea is essentially that you want to add a new term to the error loss function. Okay. So here is a general formula, and then there are many things like L1, L2, and elastic, and all kinds of things you can see. But the general idea is this. For example, if L, say I want to create a new loss, L new, which is basically, say my old loss function is this, whatever loss function you want to take. So be it, say for example, the cross entropy or squared loss or something else. This is my, say, old loss, whatever loss function you can choose. So I simply want to tweak my loss function a little bit. So by doing this thing, lambda R of W. Okay. So lambda here denotes a parameter, actually a scalar quantity. Okay. And this RW, coming to this actual expression in the next slide, is called regularization factor. Okay. And W here you can think about set of parameters that you have. Okay. So if you think about, for example, neural network, then W could be all the weights and biases and all. Okay. So that is this kind of general formula of doing these things. So the reason is that now when you know that probably you know it, that when this magnitude of these weights become very large, then the models actually tend to overfit, create some trouble for you. Okay. So you don't want to, like, you want to actually control that kind of phenomenon. Okay. So there's this one. Let's see a couple of examples. We'll probably see what happens. So first, one of these, like, there are 3-4 very popular thing that people do. So first thing is basically it's called L1 regularization. So what it is? So in this case, we have this simple rule. So this L old plus lambda is an expression L lambda greater than 0, and this L1 regularization is this. My RW in this case is going to be Ij basically magnitude of all the weights in sum. Okay. So basic idea is that you do not want to make these weights very big. Be it big negative or big positive. Both the things are bad and they tend to overfit the model. Okay.
Sir, biases will not be there here.
Generally, you do not take the biases. Yeah, but you can also take the biases. Okay. So because the reason is that, like, the weight has this particular role. You are basically multiplying these weights with the activation values. Okay, so they can actually amplify these activation values, but biases do not have that kind of effect directly. Okay, but you can also add that. Now, second, another common thing, you also probably know it, it's called L2 regularization. Okay, kind of smooth version of that, the previous one. Okay, L2. So in L2, what we have? So L nu is equals to L old plus again lambda RW, and in this case RW is going to be the sum of squares actually. Okay. So in the previous case it was the sum of all the magnitudes of these weights. In this case sum of squares. Okay, just to kind of avoid like the smoothness issue that we had in the previous case. Okay, you are taking the absolute values and so on and so on. The third case is called elastic net. It's a kind of combination of the previous two. So it's elastic net. You have this. Sorry. So in elastic net, so this, I'm not writing down the full expression here, but this is, you have the L1, this is, and then L1 plus L2, and that is it. So these are the some of the well-known things that you can use, but modern deep nets hardly use all these things. This probably can be used some other places, but deep nets have other things that we will see in a moment. Okay. Okay. So the next important thing, and I think you probably have heard these things now and then everywhere, is called dropout. And the purpose again, regularization. We want to improve the model's performance, single model performance. Okay. And dropout is again just like batch normalization. Any modern deep nets will have dropout. Okay. Everywhere basically use dropout. So what is this key idea? The key idea is that when you are training the model, you randomly drop some neurons. Okay, you just randomly drop some neurons. So drop neurons in every iteration. During every iteration, you do drop some neurons, and drop neurons from every layer also. Okay, so for example, say, and typically there is a hyperparameter which will control the probability of dropping. For example, 0.3 means you want to drop 30% of the neurons at a particular iteration. Okay, and which is kind of hyperparameter you set it. Now, why dropping neurons from every layer? Now, if you choose, for example, that I want to drop 30% neurons from my network, and if you do not do it in a layer-wise fashion, then it may happen that you may accidentally like drop all the neurons from a particular layer, and that is going to make the network completely disconnected from one another. Okay, so that is why you do this kind of things for every layer. For every layer, for example, you want to drop 30% neurons. Okay, and the dropout probability that you set will tell what percentage of neurons you want to drop. Now, in some setup, people call this retention probability. In some setup, people call this dropout probability. So you have to interpret this accordingly. So if it is dropout probability, you are going to drop 30% neurons. If it is retention probability, you are going to retain that percentage of neurons, and so on and so forth. Okay, so be very careful when you are actually implementing the things. Do not set dropout probability which is actually using as a retention probability. That might cause some problem. Okay. Okay. So let's look at this and what it happens. Okay. So what you do? So basically, when you are training this network, so this is your, for example, original network. Okay. On the left side, you can see original network. And so you decided to drop out some percentage of neuron from every layer. Okay. So here, for example, 50% neuron you are dropping from every layer. Okay, something like this is happening. So by dropout means it is not that you are dropping these neurons from the network entirely. This is not like that. Never confused on that. Okay, you are not dropping a particular neuron entirely. You are only dropping a particular neuron for that particular iteration. Okay, so for example, I decided that okay, at ith iteration, okay, my dropout probability is 0.5. So from every layer, I'm going to drop say some percentage of neurons. Okay, so I will choose. Okay, I will drop out this neuron, this neuron, this neuron, this neuron, and this neuron. These 5 neurons I'm going to drop out. So dropout means you are not updating the parameters associated with that particular neuron for that in that particular iteration, and that is it. Okay, so that is the meaning of dropout. Now it may happen that at I plus 1th iteration, okay, you are actually these neurons are active actually. Okay, because dropout doesn't suggest that you have to drop them entirely from the network. Once you drop out, you may need to use it again further. Okay, because this is done every iteration. Okay, so that is basically how you are going to perform this one. You simply switch off these neurons. You don't want to update these weights and biases associated with this particular neuron. Okay, just switch it off. Whatever value it had, you return that, but you don't update in a particular iteration when you are dropping this out. Okay. Now you can do this. All right. So some neurons will have dropped out, and as a result, you will have these lesser weights and all kinds of things going to happen. I do not know what is happening because it's absolutely random. Now, what happens during test time? Okay. During training time, we can do dropout and this and that. But test time, what do we do actually? So during test time, and you remember this, you look at this particular picture carefully, and this is very important to understand what happens because there are lots of misunderstanding on that. So at training time, a particular neuron is present with probability P. Okay, and it has its weights and everything that else you have here. Okay. Now at test time, all the neurons will be present, but you remember this factor. Whatever weight that you had after training, okay, so weight is W is a weight, and the effective weight will be P into W, where P is the retention probability in this case. Okay, because the way I am basically using this notation here, the P is the retention probability present with probability P. Okay, not the dropout probability. So as a result, so my effective weight will be this one P into W, and all these like weights will be multiplied by this retention probability. Okay, so that is how we are going to kind of take into consideration the probability of dropout which we use during training.
Sir,
Yeah, go ahead.
so can you explain once again why the test time P into W?
Okay, so when you are training, you dropped out some neurons, right?
Yes,
so
sir.
like with some probability, or rather you retain some neurons with some probability P. Okay, that means so not all neurons will contribute during training equally. Okay, so neurons which will contribute very well, for example, throughout the iteration, you would never dropped out any neuron. Okay, so because you made maximum amount of updates on that, so the weight change of for that particular neuron will be very high, right from the initialization to the termination. Okay, and somebody who, for example, didn't contribute much, its weight change also will be very low. Okay, so this factor P is basically taking into consideration that. Okay, so somebody who is contributed high will contribute high in this case. Somebody is contributed very low in the computation, you will contribute it very low in this case. Okay.
Okay.
All right.
Sir, one question.
Go ahead.
Present in each layer at each iteration, the present with probability P means that 30% you were talking, right? The 30% is the dropout probability. Then for every neuron, it will be 70% retention probability. The P will be same, right?
P will be same, yes.
So means what is the point of then multiplying with P? Because for every neuron, if it is same, then how will it affect if it is not multiplied with P?
So transformation function that you are applying is a nonlinear functions, right? You have some combination of these, and then you apply nonlinear. So if it is linear transformation, even then in linear transformation, okay. So because the main reason is I think is basically you are applying nonlinear transformation. So P into something, P into X and X will be different in nonlinear transformation.
Okay, and also, sir, why?
And one more point. Yeah, I'm coming to your question. The other question. One more point is that. So the other reason, and which I didn't mention in the previous slide, is that the P is not constant for all the layers. Okay. So P may vary from layer to layer. Maybe for first layer, the value of P is, for example, something else, 0.7. For second layer, it's 0.6 and things like that. So that can also happen in practice. Yeah, go ahead.
But P is same for each layer, right? Like
P is same for each layer. Yes, it is same for each layer.
Okay, and sir, also one thing, why we do not drop out during the test time?
Okay, so when you do not, that's a good question actually. So see, when you are dropping a particular neuron during training time, okay. So for example, think about a situation like this. Say you are running 1000 epoch and you dropped a neuron, say at 900 epoch. Okay, so before until that neuron contributed in your training, right? So if you simply drop the neuron out completely during test time, then you are losing in the contribution of the neuron completely.
Okay, yes, sir. Understood.
Right? Yeah, that's the main issue there. Okay, all right. So just quickly, couple of other things, regularization that people will do, and in these things people typically do for image processing stuff. So for example, So regularization means like you want to enhance your model performance using some kind of trick. Okay, so there is another approach people use called data augmentation. Okay, so in data augmentation, what we do, for example, this is a simple like I'm just showing CNN model. It could be another neural network and so on. So you basically have image, then you have the levels, and you apply some model, you compute loss, and then do it and whatever you want to do it. Okay, that's the typical CNN model. So data augmentation means you enhance your data set. Okay, for example, if you look at this picture of this cat, this particular picture, if the training data only has this particular picture, okay, then however smart your model is, the modern deep nets, generally they won't be able to say that this is also cat. Okay, that's a problem with deep nets and most of the machine learning problems. Even if we understand that they are cats, but the pictures or the training examples that you are giving should have highly similar things. Okay, as a result, this is a problem. So in order to address these things, what we could do, we can basically some kind of transformation we can do. So you simply rotate the image, for example, you flip this one and so on and so forth. Okay, you can transform this image, same image you take it, transform it a little bit, you change the color, okay, change the orientation, something like that, and you simply add this data into your training data set. This is called data augmentation, regularization by data augmentation. Okay. The other thing that you could do, you can do some kind of random crops and scales. Okay, by random crops and scales, what I mean, you can take part of these images. For example, you only taking the head or the eyes or the ears of a cat. Okay, you can resize these images. Okay, make it big, make it small. You sample random patches and so on and so forth from different regions, and simply take this out as separate image and then put it into your training data set. Okay, so that is how also people actually also do data augmentation things to improve the model performance. Okay. So objective is to make sure that you are going to see different parts of this input data, so that your model is basically better equipped to handle this kind of situation. Okay. All right. We can also play with, for example, the contrast and brightness of the images. Change the contrast a little bit, brightness a little bit, and so on and so forth to augment this image. There are other methodologies as well, but I'm just showing a couple of examples here in this case. Okay, you can use any kind of like standard like image processing tool to change the contrast and brightness and so on and so forth. Okay. All right. So these are all from more or less these fundamentals of deep nets, and probably Professor Advait Mitra will probably talk about the other things on deep nets like CNN and RNN kind of things. But more or less they are built upon the techniques that I discussed so far. The same techniques are going to apply. Architectural difference will be there, but you apply the same backpropagation, batch normalization, the mini Bayes gradient descent, and everything else. The same tools we use. Okay, so architecture will be slightly different. When you're dealing with image, you need CNN. When you're dealing with sequence data, natural language data, then you need RNN, stuff like that. But more or less the fundamentals of that. Okay, so okay, all right. So now we will look into another classification technique called Bayesian classification. Okay, we have seen so far various kinds of classification. Okay, logistic regression, k-nearest neighbor, neural networks, and so on and so forth. Now we are going to see how we can use the Bayes rule, okay, Bayesian statistics to do classification. Okay. So let's see. So for example, this is a simple example where you want to measure the length of a fish and decide its class. So simply you want to use the length of a fish and decide whether it belongs to Hilsa or tuna. Tuna is a very popular fish in most of the European countries and in US. Okay, so that's what we want to do, and how we should do it. Okay, so the simple way, and there is no smart feature engineering in this case, unlike neural networks. So here the feature engineering has to be done by you. Okay, so what if the first thing that we do, given this, we collect statistics from a set of, for example, Hilsa, and also collect statistics from a set of tuna. So statistics which you think will be relevant to make the decision. Okay. So in this case, for example, length, or you can use something like color or other things as well. Okay. All right. So now the distribution of fish length. Okay. Now the concept that here I'm using is called class conditional distribution. Okay. So what it is, it's a conditional probability distribution. So the probability that a particular length will be observed given that it is Hilscher, or the probability that a particular length will be observed given that it is a tuna fish. So it is called class conditional probability. Okay, because it depends on the particular class you are dealing with, and it's a conditional probability. That is a class conditional probability. Okay, and you can see this kind of picture if you have set up like numbers. So you have say 1000 tuna or 1000 Hilscher, and you measure their lengths and you simply plot it on the diagram, which is called histogram, and you are going to get that kind of probability distribution. Okay, it's pretty straightforward. You probably know, all of you know it. So what's then the decision rule in this case? Okay, the decision rule is that, for example, simplest decision rule that you can come up with is that if the length is less than equals to b, b is some kind of threshold, you can say this is Hilscher, else you can say this is tuna. Okay, that is the simplest possible decision rule that you can come up with. And this Bayesian statistics also has internally, it has these things, but it does it probabilistically. That's the only difference. It's not, it doesn't do in a hard way, but rather in a probabilistic way it does it. Okay. So then what should be the value of b? That's the boundary, okay, of this, the decision boundary in this case, for example, this numerical value b. Okay, value of b that we do. And we use this population statistics to figure out what would be the possible value of b, or the best value of b rather. Okay, so that we basically have to figure that out. All right, now let's see the decision rule and what kinds of error that you can encounter. Okay, in this. Now, for example, I measured the lengths of two categories of fishes, for in this case Hilscher and tuna, and then I came up with the probability distribution. You can see the probability distribution of the length given a fish and so on and so forth. And I can say there is some certain overlap region. Okay, that means based on the length, okay, you cannot definitively say that whether this is going to be Hilscher or this is going to be tuna, because there can be some short length Hilscher or long length tuna. That can happen in reality. Okay, so the length itself is not a very good discriminative indicator of telling that whether this is going to be Hilscher or tuna, and that can happen. Okay, so if you look at this picture carefully, now there are two possible errors in this case you can think. For example, if you choose your decision boundary be something like this I am showing in this picture, what happens is that the first kind of error that can happen, they actually tuna, but you are classifying this as a Hilscher. Okay, so the region that you can see, the area under pink curve to the left of B, anything that is falling on that region, you are basically saying this is Hilscher, but it should actually be tuna. Similarly, the other way around. Okay, you are saying that actually it is Hilscher, but you are saying this is a tuna on the other part of these things. Okay, so it happens when there are certain degree of overlap between distribution of the data that you are dealing with. Okay, and so the main thing is in this case that you have to choose the good decision boundary or decision rule in this case. Okay, for example, the good value of b. What is the good value of b so that I can minimize my error? Okay, that's the main question that we should be asking ourselves. All right, so here the good value of b should be in this particular picture is b star, which is kind of, you can think somewhere in the middle. Okay, and this is I'm calling the optimal value of b, at least for this particular picture. Okay, so this optimal value of b will give us the minimum possible error. Okay, so that is something you can figure that out. That is actually a good thing to do. What is the process that you need to follow when you do this kind of thing? So at least for this particular example, you measure the lengths of a population of two fishes, for example, Hilscher and tuna in this case, and make sure that the number of such things are basically very high. Otherwise, you are not going to get good statistics out of this data. Second thing, what you have to do, you have to estimate the class conditional distribution for Hilscher and Tuna classes respectively. Because class conditional distribution is going to give you the distributional picture, the shape of this distribution, okay, from this data. Then try to find the optimal decision boundary from the distribution, which will minimize this error. Something that we have seen, which is somewhere in the middle. Okay. And then once you have these things, you can simply apply the decision rule to classify a new fish or new species, whatever you are dealing with, to say that whether this particular species or fish is going to belong, is going to be in one class or the other class. Okay, based on this decision boundary, which is B star. Okay, so that is more or less the steps that we follow in, like, this Bayesian learning. Okay, now there are many factors that can come into play. Okay, for example, location and time of experiment in this case, that when you are collecting this data. Okay, so location and time can play an important role in this case. It can actually dismantle this data, nature of this data. For example, during monsoon season in Calcutta, you are going to get more Hilscher, few Tuna. Okay. Now in California in winter, you are going to get more Tuna but less Hilscher. Okay. Second thing, even if like 2 feet fish is likely to be Hilscher in Calcutta, and a 1.5 feet fish may be Tuna in California as well. Okay, so this factor also can, like, come into play when you are basically doing this kind of experiments. So here the thing that we use is called Apriori probability. So what it tells us that we want to use some prior knowledge about a particular thing. Okay. So what it is that without measuring the length, can we guess something about the class of fish? Okay. So for example, whether if it is from Calcutta, a particular fish is from Calcutta, then the prevalence is that it's going to be Hilscher is much higher than Tuna. Okay. If it is coming from California, the prevalence of this particular fish is going to be much higher for Tuna than Hilscher. Okay. So whether we can use this kind of knowledge into our model, additional knowledge, and this is called a priori probability, some a priori knowledge, without even measuring the length. Once you get a fish from Calcutta, without measuring this thing, if I ask you whether this is going to be Tuna or Hilscher, without doing anything else, you probably will say this is perhaps going to be Hilscher, because you have not seen too many Tuna in Calcutta. Similarly, the same thing for Hilscher in California. Okay, so this is called a priori probability. So a little bit of like statistics that, and say a priori probability you generally measure based on your prior experience, like say take 50 years of data and say you count how many times that you have seen Hilscher in Calcutta, how many times you have seen Tuna in Calcutta, and then simply do it in this way. Okay, and you are going to use this a priori probability along with the class conditional probability in our decision making, okay, in Bayesian statistics. Okay, so we take a break and then we come back and then we discuss about the other things. Okay, so I hope you can hear me and see my slide.
Yes.
Okay, all right. Okay, so what we want to do then in Bayesian classification is that we want to use these two, a priori probability as well as class conditional probability that we have seen in the previous slide together to make the decision. So let's see how we do this. So the classification decision, as I said, is a product of the a priori probability and the class conditional probability distribution. Now, so what's the posterior probability, which is basically the Bayes rule, says that okay, given the length, particular length, I want to estimate the probability that whether this is going to be Hilsha, and vice versa, I can predict whether this is going to be Tuna. Okay. Now, this is going to be a simple Bayes rule I'm applying. So it's going to be the probability of Hilsha into the class conditional probability into divided by the probability that the length is going to be 2 feet. Okay. Now, simple straightaway Bayes rule I'm applying here in this case. Now, if you look at this carefully, this expression is absolutely constant. Okay. So the probability, the posterior probability is equivalent to the a priori probability and the class conditional probability. So we can basically discard this one altogether when you're taking the decision, because probability will be divided by some factor, constant factor. So do not need this actually. That's why I'm saying in the approximation of this one. It doesn't change that probability of belongingness to a particular class. So let's take a deeper look into it. So what we do then, we consider the product of a priori and class conditional probability factors. So the Bayesian rule that we have seen. Now 3 things that you need to know carefully. One is called the a priori probability, which is without any measurement, based on just location, time, etc., some prior knowledge, whether you can guess about the class membership. Okay, that is the a priori probability that you have seen. Second thing is called class conditional probability, and it is that given the fish belongs to a particular class, what is the probability that its length is 2 feet? And that is why I am calling this class conditional probability. You are using the class information to measure that what's the probability that the length is going to be 2 feet. Okay. And third is the posterior probability. So given the measurement that the length of the fish is 2 feet, what is the probability that the fish belongs to a particular class? Because we are actually trying to measure this one finally, the posterior probability. Because the observation that we have is the length of the fish, and from this we want to predict whether this is going to be in Hilsha or in Tuna. That's the posterior probability. Okay. So these 3 concepts more or less we use all the time in Bayesian decision making. This is not only for classification thing, for other applications as well, all can use this one. Okay, so these 3 important probabilistic concepts that we use. All right. Now coming back to our original, this main picture, that we have to figure out the B star, okay, optimal value of B, the boundary condition, for which we will have the minimum amount of error. Okay. So this error is basically, if you compute the error on the 2 classes, okay, the amount of error will be equal. And what would be that, the B star, so that we can have that kind of situation. Okay, this is called the Bayesian error or Bayes error, minimum error probability. Okay, so but finding this decision boundary B star is intractable, it's very difficult. Okay, so nearly impossible. Okay, so what we do instead, we can simplify this whole thing and then we can actually do maximum a posteriori probability. Okay, so what we do in this case, and just on the next slide I'll have this formulation. So you classify an object into a particular class with the highest posterior probability, and that is it. Because we cannot find out B star, okay, so we can basically use maximum a posterior probability to do that. So here, for example, when you are doing the multi-class classification, if you have, say, for example, multiple classes in your data, hilsa, tuna, shark, and whatnot in this case. So, of course, you want to measure the probabilities of the class conditional probability, the posterior probability, posterior probability for all these classes, and based on that, you can simply decide in which class it has the highest probability of belongingness. Okay. So quickly, little bit of some pictures about the decision boundary and so on and so forth. So for example, I have two features in this case, weights and length. Okay, and so one class is hillsa and the class is tuna. So I'm just showing here the decision boundary, which will give you the minimum amount of error. Okay, and so decision boundary is called the class separability. Now, two spherical classes, okay, can have the different means but have the same variance. Okay, so here the decision boundary is a perpendicular bisector of the mean vectors. So if you take the mean vector, okay, connecting the two centroids, and then you take the perpendicular bisector, you can have this decision boundary. But unfortunately, in real life situation, you cannot claim all these things, that whether the two classes will have the same mean and kind of different means and variance, and they will have the same kind of distribution and things like that. But if you have that, you can basically use this kind of thing to figure that out. Now, we need to use some kind of distance measures. Okay, for example, given a particular sample, test sample, and if we have a distribution already known from the training samples, we have to measure some kind of distribution distance measures. Okay, so there are several things. We already touched upon some of the things. So when you are dealing with two vectors, you can use Euclidean, Minkowski's, etc., etc. When you have a vector and a distribution, okay, you have a vector given and you have got a distribution, and you have to basically measure the closeness of that. Okay, in that case, you can use a mononomial distribution, a mononomial distance measure that we talked about. Okay. Now, when you have two distributions, two probability distributions, okay, and you want to measure their similarity or dissimilarity, then you can use Kullback-Leibler divergence, or in short KL divergence. Okay, so depending upon the situation that you're dealing with, you have to choose which particular thing you are going to use. Okay. So here is a little picture and one question that I am showing in this slide. Now, which distribution is closer to X? So what would be the answer? Which distribution is closer to X? So X you can see on the left side. Sorry, which one?
The pink distribution.
Pink distribution. Yeah, that's right, pink distribution. Now in this case, which distance measure you want to use?
Vector and a distribution.
Okay, so it has to be vector and distribution because the X is in terms of vector, and then you are basically trying to measure the probability of that here. So the right thing to apply in this case is mononomial distance. Okay, no Euclidean, no Minkowski, no KL divergence. Okay. Now, the other kind of decision boundaries that you can think about it. Okay, one is big, another is small, and still is.
Explain why mononomial distance is the right thing.
Why mononomial distance is the right thing to do in this case?
Yes, sir.
Okay, and that's just the nature of the distribution, the distance measure. You can just take into consideration about that. Okay.
Why not Euclidean?
So the problem of Euclidean is that when you are dealing with, okay, so basically the probability distribution and the vector, okay, they are not compatible on the same scale. Okay, because X is a vector of some feature values, and another one is probability distribution. So because they are not same scale, you cannot use Euclidean or Minkowski, etc. Okay.
Okay, sir.
Right. So the other kind of decision boundary that you can think about it, like the two elliptical classes. Okay, can be depending upon the data that you have. Equilateral classes that you have having different means and variances. Okay, and so a possible decision boundary could be parabolic of nature. Okay, so if you have the exact shape of all these things, you can probably figure out the best decision boundary. But unfortunately, in real life data, you do not have that kind of things. So here the Bayesian decisions actually come into play very well. Now a little bit of mathematical underpinnings of Bayesian classifiers, and this is coming directly from the normal Bayes rules. So what we want to do, that we want to compute the posterior probability. Okay, so what the given set of feature values or observation a1, a2 up to an, okay, and we want to decide that what is the probability that it will belong to class C. Okay, that's what we want to do. Given the observation, we want to measure the probability of that particular observation will belong to class C. That's what we want to do. Okay. So inside the red box, just straight simple application of Bayesian rule. Okay, I'm not explaining. Just probably you have seen in higher secondary. So just straight application of Bayes rule, you can going to get this kind of thing. Okay, and you choose the value of C that maximizes this probability. Okay, so basically you compute probability for all classes and simply take the class having the maximum probability. Okay, so which is equivalent of choosing this expression which we have seen before, because we are actually removing one part, okay, which is constant. So we simply do that. Okay. So again, the main issue that here in this case is that the PC, okay, is the apriori probability. So that is kind of given a particular location or some prior data, you can have that estimate. Okay, but from this data, we really want to estimate this one, this expression, the class conditional probability. Okay, so probability that the observation is coming from a particular class conditional probability that you have to basically estimate. Okay, and that is what we do. If we can do that, then everything is basically done. All right. Now, quickly, some examples of Bayesian classification. You can see this data, like bunch of attributes, and then you have the classes, mammals, non-mammals, and so on and so forth. Okay, and given a test sample, for example, on the below you can see this test sample, give birth, can fly, live in water, have legs, and things like this, and you have to figure out the class conditional, the class of this particular sample. Okay. And so you can basically compute these probabilities for all these classes, and depending upon that, the value, maximum value, you can say whether this is something one class or the other class and so on. Okay. Now, the issue is that we are dealing with, in real life, we are dealing with multivariate data. Okay. For example, most of the time, the samples that we'll be dealing with have multiple features. Okay. So it's multivariate data. Now, what is the main trouble with estimating multivariate class distribution? Okay. The main issue that we encountered is that typically if the number of the value of the dimension of this data is very high, then you need to have large number of samples to estimate these probabilities very well. Okay, and that is a problem. So always has been the problem. Okay, so data sparsity problem. It's called curse of dimensionality. Okay, so you have too much of data. Need too much of data to estimate the probability reliably if you have the high dimensional feature vectors. Okay, that's the main issue we always encountered. So how we simplify that? We simplify this one by assuming that these feature values or the features are actually independent. Okay, for example, the length and weights are independent. Not absolutely realistic, but we can kind of make these assumptions to simplify our computation. Okay, so if we do that, then basically you can simplify the whole computation. So then the joint distribution that we are observing, joint distribution of all the features together, is now basically a product of the marginal distribution, the individual distributions. Okay, and therefore you can, from the data, you can estimate quickly the marginals compared to the joint distributions. Here is this actual expression. Now, assuming that the features here A1, A2 up to AN are the features, so they are independent. Okay, so the joint probability now becomes the product of the individual probabilities. Okay, so probability of A1 given Cj, A2 given Cj, and so on and so forth. And we can then very easily estimate all these individual probabilities, class conditional probabilities of these individual attributes. Okay. Once you have the data, then you can go and basically estimate all these things very, very easily. And depending upon the value, the probability values, you can basically choose the class having the maximum probability. Okay, that's the maximum a posteriori probability. Okay. So here are some of the examples that I basically have shown. You can just take a look offline. That's just simple numerical examples that I mentioned here, so you can see it. But anyhow, more substantive issue. So ultimately, we have to estimate this class conditional probability. Okay, given a particular observation, value of a particular attribute, given a particular class, what is the probability that this value is coming from that particular class? Okay, so in a sense that how likely a feature value appears in a class. Okay, now a little example that I'm showing on the right side. So feature can be of two types. It could be discrete valued and it could be continuous valued. Okay. Now the question is that for both the situations, both the scenarios, how we can compute this class conditional probabilities for both discrete valued features as well as continuous valued features. Okay. So let's take a look. So first of all, we try to handle the situation for discrete valued features. Okay. So for discrete valued features, a possible thing would be, and if you look at this expression carefully, that given a particular class Cj, what is the probability that the value for feature xi is v? That's what I'm trying to figure out. Okay, and so if you apply simple probability rule, you can see in the numerator that the number of times v appears in ith feature of class Cj. For every class, you have the numbers. So you simply go to class Cj and then see how many times the value v is appearing. Okay, divided by total number of sample in that particular class. Just the plain maximum likelihood estimation that we apply in this case. Okay. Now, what is the problem with this estimation? The problem with estimation is that now, say you want to predict the class of a person having height 5.8 and weight 7.72, and hair is long. So this is the observation that you have. Okay, you want to predict the class of that person, whether he will be male or female. Okay, the person will be male or female. That's what you want to do. Okay. Now in this case, height is a continuous valued attribute. Weight 72 is you can think about continuous valued attribute, but here is a discrete valued attribute. Okay, and for this particular example, I am focusing only on discrete valued attribute. Okay, so continuous valued attribute. Next slide, I will describe. So okay. So the probability that the person will be male, given male, he will be person, okay, is that the height is equals to 5.8 given male into weight is 72 given male into hair is equals to long given male. Okay, so just like individual probabilities. Okay, the marginal probabilities. And anyway, so height, weight, we can basically estimate. But the important thing that I'm trying to focus on this particular slide is that how you estimate the probability for the discrete valued attribute. Now, look at this expression, the previous expression, the estimation rule. Now, because my data doesn't say, the little data that I have, because it doesn't say that there is no individual, no male who has long hair in my data. So this probability, this one, if I simply apply this rule, okay, is going to be 0 because my data does not have that kind of information. Okay, nowhere in my data, in my little training data that I have, that a male person has long hair. But in reality, it can happen, right? A male person can have long hair. Only because I was not able to collect the data appropriately, or maybe I took little bit of data, not much data, that is basically happening. Okay. So irrespective of whatever signals that I am receiving from height feature and weight feature, okay, This simple little mistake here in estimating the hair is long given male is spoiling the show. Okay, everything else. So if probability becomes 0, that means you're going to say that, okay, this person is not going to be male. Okay, that's problematic thing. Okay, so in this kind of situation, a single indicator, if a single indicator says bad things, then the whole thing can become 0. Okay, and that is a problem. So we need to address this kind of situation, and we address this using a thing called the smoothing approach. Okay, so smoothing means you adjust this probability a little bit just to avoid 0. Okay, by adding some number. There are lots of smoothing formulas. So one of these formulas that I am mentioning is here, that you introduce another constant called C, which is greater than 0, and so basically you adjust a little bit. Observed frequency, how many times you observe in the data, plus C by plus sample, number of samples, plus C into number of unique values, and so on. So this is one of this formula that you can use. There are other formulas as well, smoothing, but general idea is basically you have to smooth these values a little bit to avoid the 0 probability problem. Right, so if you apply for this one, you are going to get this kind of value. You can just take this example offline and try to understand. All right. Now the continuous valued features. We talked about discrete valued features. Now continuous valued features. How we can estimate the probabilities. And one of the simplest way to do it, that and which is typically this assumption that we make, that feature values follow Gaussian distribution, normal distribution. So you have 10 features, for example, the continuous valued features. And every feature is going to follow the Gaussian normal distribution. Okay. So if you have that, then for every class and for every feature, you have a Gaussian distribution. So you can compute the mean and variance, standard deviation, okay, for every class and for every feature. Okay, and then you can apply this rule straight away. Once you have the distribution function known, then you can straight away apply this distribution function to figure out this probability values for this. Okay. All right. So yeah, I believe. Yeah. So essentially, what you need to compute in this case, that you need to compute the mean and variance for all the classes separately and for all the features, of course. And then you simply apply this one to estimate the probability values. Okay. All right. So that's it from my side. If you have any question, any clarification, anything you need, you please let me know.
Excuse me, sir.
Yeah, go ahead, please.
Can you please put up the slide, the last slide once again?
Oh, last slide once again. Yeah, sure.
I mean, I don't have any question. I just want to look at it.
Yeah, this one, can you see?
Yes, thank you.
Okay, go ahead. You have a question, or you wanted to see this?
No, sir, just wanted to see it.
Oh, okay, all right, all right. Yeah. All right. Okay.
Sir.
Yeah, go ahead, please.
Sir, why would we prefer using this Bayesian classifier if you already have deep neural networks? And if the problem was a priori probability, then maybe in the deep neural network itself, we can give it an input whether the location is Kolkata or something, to keep that in mind. So if deep neural network will perform better than this, then why would we even use this method?
Yeah, so that is the question that always crossed my mind as well. So the reason is that the discipline evolved, machine learning discipline, and there are lots of classifiers. But some situation, for example, neural networks are good when you have plenty of data. Okay. So if you do not have plenty of data, like lots of data, then neural network probably is not a good thing to do. So there you probably want to use the classifier which is not that data hungry, number one. Number two, neural network also is very computationally intensive. For example, some organization or some place, those who do not have that computing power, you probably want to go for cheaper methods, very efficient method. Okay. So in that scenario also you can prefer the Bayesian classifier compared to neural networks. Okay. Third, explainability. Because the Bayesian classifiers are simple, you can basically look at each class conditional probability distribution and try to understand, okay, what went wrong when something goes wrong. That is something is extremely difficult in neural networks. So for explainability things, in particular medical diagnosis and things like that, when you actually get into these real values, what is happening, what is the class conditional probabilities, then that can also be very, very useful. Okay. So in some situation you prefer because of this inherent advantages of Bayesian classifiers.
Okay, sir, got it.
Yeah.
Sir, in the regularization slide, can you just put it once? I have a question there.
Sure. Regularization, right? Okay, let me just regularization. Which part? And this?
Yeah, there was a plot, two plots that
Okay, sure, yeah. Okay.
loss and accuracy.
Yeah, sure. I'm just sharing the screen. Yeah, this one.
Yes, sir.
Yeah.
Sir, here my question is, as we are increasing the number of epochs, so at each epoch we are getting some updated value of the weights and biases, right?
Right.
So as if we are increasing the number of epochs to a large extent, then there is a huge difference between the train and validation accuracy.
Right.
So why can't we just like not train for that number of epochs, only for a small number of?
Well, how do you know that the number of epochs is good for you? Because sometimes larger epoch means better training. Okay, because you are going to optimize your network very well. So how do you know that, okay, say 2,500 epochs is good compared to 5,000 epochs?
Like we can check the validation accuracy, and if it is going down, then we can sense that there is an overfitting.
Well, I think that is not a very good. So essentially, you have to what you have to do basically. Then you have to run multiple times. Okay. So every time and see if you want to check during training, if you want to check the validation accuracy, and validation accuracy has to be checked on a number of samples. So time is going to be very, very high. Because every time you train a particular epoch, you have to compute this accuracy on the validation set, you come back and do it.
Okay, so using the regularization parameter can check it for any case. Is it that?
This is not a foolproof guaranteed method. It can control to some extent. So these regulation techniques, nobody can guarantee that you are not going to have overfitting and things like that. But the effect will be severe, less severe. So none of these methods actually guarantee. Okay, that okay, there won't be any problem.
Okay, sir, understood.
Yeah.
Sir?
Yeah, go ahead.
In this case, like in this graph which was shown, sir, so like we could have stopped somewhere like at 7,500 epochs itself, right? Like when we got to know that there is not much increase.
Yeah, people do that. People do that. This is called early stopping. Okay, so in standard machine learning terminology or deep learning network, it's called early stopping. So that's what the previous student and you are suggesting, that you train and then at the same time you measure the validation accuracy, and when you are saying that okay, there is a huge difference, you basically stop. Okay, so that is possible, but yeah, and some people do that. But what I'm trying to suggest is that it has its own additional burden. Okay, so every time, after every epoch, you have to compute the accuracy on the validation set, which means drawing all this inference and doing forward pass, for example, if you are training network, okay, on the all the validation test set and so on. But what you're suggesting is not uncommon. Some people do that. This is early stopping in literature.
Okay, sir, got it.
But there is a problem with early stopping as well. I tell you why this is the problem. So early stopping prefers the common examples generally. So if you have say in your data set that there are 95 very similar examples, there are 5 very rare examples. Okay, so your early stopping will focus on all 95 examples and it will ignore the 5 rare examples because your accuracy is very high, you will say this good. But this kind of training and approach is not good for safety critical systems, for example, in medical domain or in aircraft flying, okay, or in automated driving. So there you need to have very, very high accuracy. You actually want to focus on the rare examples as well. Okay, so the early stopping is a problem for this kind of scenario, where safety is very important.
Okay, sir.
Yeah. Okay. So I won't be taking any other class. Maybe I can take one later on. I'm not very sure. But from next week, Professor Oddoy Mitro will be